Have you ever looked at a self-driving car or a satellite and just wondered, how do you even begin to build something that complex? It all starts with a blueprint, but not the old-school paper kind. We're talking about a digital blueprint. And today, we're diving into the two essential languages used to design our entire modern world, UML and SysML.
So what do they have in common? A truly mind-boggling level of complexity. You know, a self-driving car isn't just a piece of software. It's this intricate web of sensors, mechanics, and millions of lines of code, all working together. If there's a single mistake in that initial plan, one tiny miscommunication between the hardware and software teams, the results could be, well, catastrophic. That's why the blueprint is absolutely everything.
So before anyone writes a single line of code or cuts a single piece of metal, engineers need a way to see the whole system. They need to analyze it, talk about it, and make sure every single person is on the same page. They need a shared language, a formal blueprint.
And that's where a modeling language comes into play. Just think of it like an architect's blueprint for a skyscraper. It gives everyone a universal set of symbols and rules. So the hardware team, the software team, the electrical team, they're all speaking the exact same language. It makes these incredibly abstract ideas solid and tangible.
Our story really begins in the world of pure software. For decades, the undisputed king of software blueprints was a language called UML, which stands for the Unified Modeling Language.
Okay, so this chart here is going to be our map for the journey today. Let's start over on the left with the original titan of design, UML. For a long, long time, this was the absolute gold standard for architecting software systems.
And its focus was laser sharp. It was all about one thing and one thing only: software. How is a program structured? How does it behave? How do all the different pieces talk to each other? It was built by software developers for software developers, period.
Now, UML gives developers two main types of tools. First up, you have the structural diagrams. The best way to think about these is as the static blueprint of the software. It's like the anatomy of the program. They define all the fundamental building blocks like classes and components and show you exactly how they all fit together.
And then, on the other side of the coin, you have the behavioral diagrams. So, if the structural diagrams are the anatomy, these diagrams show the body in motion. They map out how data flows, how users interact with the system, and how the software actually behaves from one moment to the next. This is the physiology of the program.
And for a long time, UML was perfect. It did its job incredibly well. But the world changed. The most exciting, the most challenging products weren't just software anymore. They were becoming something much, much bigger.
I mean, think about a modern car. It has dozens of powerful computers, sure, but it also has a physical engine, brakes, and a complex power system. So how do you create a blueprint that shows how the brake sensor software is supposed to talk to the physical brake hardware? UML, because it was so software-focused, just didn't have an answer. It didn't have the vocabulary.
And that gap, that need, created the perfect opening for an evolution, a new language built for this new, complex reality. And that's where SysML, the systems modeling language, steps onto the scene.
This slide really shows you the core evolution in a nutshell. UML is very introspective. It only really cares about the software world. SysML, on the other hand, is extroverted. It was built from the ground up to model how software interacts with hardware, with physical processes, and even with the people who use the system.
So how did SysML pull this off? Well, what's so clever is that it didn't just throw everything out and start from scratch. If you look closely, you'll see SysML, over on the right, actually borrows a lot of UML's proven diagrams. It then adds a whole new layer of tools on top, specifically for systems engineering. It's an evolution, not a revolution.
So it keeps all the useful tools for mapping out how things work, but it adds some serious game changers. For the first time, engineers could create diagrams that included real-world physical constraints, like power consumption or weight. But the real superstar, the biggest upgrade of them all, is the brand new requirements diagram.
And this right here illustrates why it's such a big deal. The requirements diagram is like the master connector. It lets engineers formally write down every single thing the system has to do, like the battery must last for 10 hours, or the airbag has to deploy in under 20 milliseconds. And then it links those rules directly to the parts of the model that make them happen. It makes sure nothing ever gets lost in translation.
So you've got these powerful new blueprints. How do they fit into the bigger picture of actually building something?
Well, SysML is a key part of a much broader engineering philosophy called Model-Based Systems Engineering, or MBSE. And this is the modern workflow for building complex stuff.
And this workflow changes everything. You start with your requirements, you build the digital SysML model, and then, and this is the magic part, you simulate it. You can test the entire system digitally, finding huge design flaws that would cost millions of dollars to fix if you found them in the real world. It's all about catching mistakes when they're just pixels on a screen, not concrete and steel.
Okay, so we've dug into some pretty technical details here, but let's zoom out. Why is this shift from a software blueprint to a full system blueprint so incredibly important? What's the real payoff here?
Well, the payoff is that we can actually build things like self-driving cars and satellites without them failing. By using SysML and this MBSE workflow, the team building the car's camera hardware and the team writing its object recognition software are working from the exact same plan. This shared blueprint is the hidden engine that makes our most advanced technology possible.
It really makes you wonder, doesn't it? I mean, from smart cities to interplanetary missions, these systems are only going to get more complex. So the real question is, what are we going to be able to dream up and build next now that we finally have the right blueprints to design it?